Let's use the Nernst equation to calculate the EMF, or the potential, of an electrochemical cell under these non-standard conditions. I can tell that it's non-standard because the concentration of the ions are not at 1 molar. Rather, the zinc ion in this particular cell is at 1.5 molar, and the iron ion is at 0.1 molar. First of all, you need to recall the Nernst equation is the cell potential at non-standard conditions is equal to the cell potential at standard conditions minus 0.0591 divided by N, the number of electrons that are transferred in this particular per mole reaction, in this particular reaction, times the log base 10 of Q, the reaction quotient. Q. Okay, so first of all, we need to identify what's undergoing oxidation here and what's undergoing reduction, and we need to calculate the standard cell potential. And so in this case, we have the oxidation is on the left in this format. So we have zinc going to zinc ion plus 2 electrons, and we have iron being reduced from the iron in the plus 2 state to iron solid. Okay, so in this case, 2 electrons are being produced and 2 electrons are being consumed. So the transfer electrons here, the N is going to be equal to 2. We need to look up the standard reduction potentials for these half reactions. And remember, I'm going to write down the reduction potential straight off the table. And for zinc, the reduction potential is negative 0.76 volts. And for the iron 2 to iron, it's negative 0.44 volts. So in this case, our standard cell potential is equal to the reduction potential at the cathode minus the reduction potential at the anode. And so that's going to be at the cathode, it's going to be the reduction reaction is negative 0.44 volts minus the reduction potential for the anode, which is negative 0.76 volts, which is going to be the same as plus 0.76 volts. So the standard cell potential here is equal to 0.32 volts. Okay, so we have the standard and we have the N. In this case, N is equal to 2 electrons. So Q, I need to write the overall reaction balance so I can make sure that I have my Q expressed properly. Fortunately, in this case, well, it just makes it easier. The zinc is already balanced and the electron flow is already balanced. So the overall net reaction is just the sum of those two reactions there. And so the overall balanced chemical reaction is just zinc plus iron 2 plus goes to zinc ion plus iron solid. And so in this case, the coefficients are all 1, and Q is equal to the concentration of the products raised to the power of the coefficient. So the product here is just the zinc ion, because the iron is activity of 1, and divided by the reactant, which is the iron 2 plus. And so the concentrations for this particular cell, for the Q here, it would be the zinc is 1.5 molar and the iron is 0.1 molar. Okay, so now I've got my Q, I've got my standard E, and I have my N. I can plug all these into the Nernst equation. Right here, so E, I'm going to write it again right down here. E is equal to the standard cell potential, which is 0.32 minus 0.0591 divided by 2 times the log base 10 of 1.5 divided by 0.1. And when I plug all that into my calculator and calculate the new E under non-standard conditions, it's going to equal 0.29 volts. So under standard conditions, the cell potential would have been 0.32, but under these non-standard conditions, the self potential is a little bit lower. It's 0.29 volts.